Hello. This example discusses a circular loop of wire collapsing in the presence of a magnetic field. So let's have a picture describing the effect. So this is a magnetic field. We choose this to be going into the page, and we have a circular loop of wire in this magnetic field. It is given that this circular loop is collapsing. That means to say the radius is decreasing in time. And let's say that's the radius r at an instant that we are discussing. R is a function of time, and velocity, or the rate at which the r is changing with respect to time, is given to be 72 centimeters per second, or 0.72 meters per second. As the radius decreases, it is clear that the area would decrease, and if the area decreases, the flux decreases. So let's first discuss what's the direction of the induced current. So the first argument we make is that the flux is decreasing. Flux of the magnetic field is decreasing because the area is decreasing. Remember, flux is magnetic field times area. If the flux is decreasing, Faraday's law states that the system will try to increase the flux. It will oppose this feature that the flux is decreasing. So it will try to increase the flux. And the way it will do it is that it will try to induce a magnetic field. So if this was the original magnetic field which is going into the page, the system will try to induce a magnetic field. So induced magnetic field has to try to increase the flux, so that means it has to create a magnetic field in the direction of the induced is along the direction of B. So let's represent that here. So this is the direction of the induced current. So it's B induced inside the loop. If we need to have an induced current inside the loop pointing downwards, we need using the using the direction of the current given by the second right hand rule. We can calculate what should be the direction of the current. If the direction of the current is in the clockwise direction, when we hold it with the thumb pointing in the direction of I, the fingers at the center of the loop will be pointing inward. So that will be your direction of the current. So I is clockwise. In the configuration shown. Notice that since it was not really given in the problem as to whether magnetic field is going into the board or coming out of the board, the only requirement is that the loop has to be perpendicular to the magnetic field. So it was very valid to have chosen B to be coming out of the board, and in that case the whole thing would have been reversed and the current I would be going counterclockwise. Both with respect to the magnetic field, both answers are right. Relatively speaking, it should be consistent. So in this particular diagram, since the magnetic field to begin with is going into the whiteboard, and the current is is clockwise. So that's the direction of the current that's needed in part A. In part B, we are asking what is the effective voltage associated with this current. So in part B, we begin by saying that the area A of this loop is, it's a circular loop, so it's pi r square, where r itself is time dependent. Right? That's the time dependence. And the flux of the magnetic field is B times the area times cosine of the angle between the area vector and the magnetic field, which is 90 degrees in this case. Area vector is perpendicular to the magnetic field that's given to us. So that means the angle between the magnetic field and the area vector would be 90 degrees. Sorry, said it wrong. This should be 0 degrees. So again, the area vector, so area itself is in the plane, magnetic field is going into the page, P is going into the page, area, the plane of the area is in the plane. That means the vector, which is perpendicular to the plane of the area, will be going into the page, and the angle between the area vector and the magnetic field will be 0. So that's equal to cosine of 0 is 1. Area is pi r squared, so it is p times pi times r squared. The effective voltage that's induced is given as the negative derivative with respect to time of the flux. So negative derivative of the flux, which is magnetic field doesn't change in time. It's only the r that changes with time. So we have b times pi, and the derivative of r squared is 2 times r, but r itself has a time derivative to it. So using chain rule, we have dr by dt. That's the velocity, the rate at which the radius is changing. So it is minus b times pi 2 times r times velocity v, where velocity is the rate at which the radius is changing with time. We are interested in the effective voltage. The negative sign here means that the induced current is opposing the system. So as far as effective voltage is concerned, we can talk about the magnitude of that quantity. So that's P times pi times 2 R. Putting in the numbers given in the problem, we have magnetic field to be half a Tesla, pi 2 times, and this is the effective voltage induced when the radius is exactly 15 centimeters. As the radius decreases, this induced voltage also decreases. It is a radius dependent quantity. So it's 15 centimeters in meters, it will be 15, 0.5 meters. And the rate at which the radius is changing is 72 centimeters per second, which is in meters per second, 0.72 meters per second. This comes out to be equal to pi times 0.15 times 0.72. 0.15 and 2 cancel out. So that's 0.34 volt. So effectively, if we take care of the direction also into the problem. So there is a, oops, so it's best to draw that as a circular loop itself. And the direction of the current is clockwise. So the V effective is basically this. Since it's a single loop, it is okay to associate a effective voltage in the diagram. That is all that is asked. I'll stop sharing and then stop the video.